Deep within the Princeton University archives, locked away in a vault that few scholars have ever accessed, lies a collection of handwritten notes that reveal the greatest physicist in history wrestling, with a terror so profound it consumed his final decades. These aren't the celebrated equations that made Einstein famous. These are the calculations he tried desperately to prove wrong, mathematical predictions so horrifying that he called them ugly and unphysical, and spent 20 years attempting to disprove them. What you're about to discover changes everything we thought we knew about Einstein's relationship with his own greatest achievement. Picture Einstein in his Princeton office in 1939, silver hair disheveled, surrounded by crumpled papers covered in frantic calculations. His hands shake slightly as he writes equation after equation, each one leading to the same impossible conclusion. Outside, the world teeters on the brink of war, but inside this quiet study, a different kind of battle rages. Einstein is fighting against his own theory, desperately seeking mathematical proof that the universe cannot possibly contain the cosmic nightmares his equations predict. He's searching for evidence that black holes cannot exist. To understand the magnitude of Einstein's terror, we need to journey back to 1915, to the moment when he first unveiled general relativity to an astonished scientific community. For over 2 centuries, humanity had lived comfortably with Newton's vision of gravity as a simple attractive force between objects. Newton's equations worked perfectly for almost everything, from falling apples to planetary orbits. But there was one tiny, persistent problem that had puzzled astronomers for decades. The planet Mercury refused to behave according to Newton's predictions. Its orbit contained a small but measurable error that no amount of calculation could explain away. Einstein realized that this seemingly minor discrepancy pointed to a fundamental flaw in our understanding of reality itself. What if gravity wasn't a force at all? What if it was something far more profound and strange? In one of the most revolutionary leaps in scientific thinking, Einstein proposed that matter and energy actually warp the fabric of spacetime itself. Imagine a vast, invisible trampoline stretching through the cosmos. Place a bowling ball in the center, and the trampoline curves around it. Now roll a marble nearby. The marble doesn't get pulled by any mysterious force. It simply follows the curve created by the bowling ball's presence. That curve is gravity. This vision was so radical, so counterintuitive, that even Einstein sometimes struggled to believe his own creation. Yet the mathematics was undeniable. His field equations described a universe where space and time were flexible, dynamic, responsive to the presence of matter and energy. Massive objects like stars and planets created dimples and valleys in the cosmic trampoline, and smaller objects followed these curves in what we perceive as orbital motion. The theory explained Mercury's anomalous orbit perfectly. It predicted that light from distant stars would bend as it passed near the sun, a prediction confirmed during a total solar eclipse in 1919. Einstein became an international celebrity overnight. But hidden within his beautiful equations lurked something that made Einstein's blood run cold. Just months after he published General Relativity, a brilliant German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Despite the chaos and horror of trench warfare, Schwarzschild found time to wrestle with Einstein's complex field equations. Using only pencil and paper, working by lamplight in a war-torn landscape, he discovered an exact mathematical solution that would haunt Einstein for the rest of his life. Schwarzschild's calculations revealed that if you compress enough mass into a sufficiently small region of space, something extraordinary and terrifying happens. The curvature of spacetime becomes so extreme that it creates a point of no return, a boundary in the cosmos beyond which nothing, absolutely nothing, can escape. Not matter, not energy, not even light itself. He had mathematically proven the existence of what we now call the event horizon, the surface of a black hole. But that wasn't the worst part. At the center of this cosmic trap, Schwarzschild's equations predicted something that violated every intuition about the physical world. They described a point of infinite density and infinite gravitational pull, a singularity where the very laws of physics break down and lose all meaning. To a physicist, infinite is more than a mathematical curiosity. It's a sign that something has gone terribly wrong with our understanding of reality. Einstein was horrified. He had created the most successful theory in the history of physics, a framework that explained everything from the smallest planetary perturbations to the largest cosmic phenomena. Yet embedded within his masterpiece was this mathematical monster, this prediction of a place where the universe itself seemed to collapse into impossibility. He couldn't accept it. He refused to believe that nature would permit such cosmic aberrations to exist. For the next 2 decades, Einstein devoted enormous energy to proving that black holes were merely mathematical artifacts with no physical reality. He argued that the immense pressures involved in stellar collapse would prevent any star from shrinking all the way down to a singularity. There must be some unknown physical law, some quantum mechanical effect, some fundamental principle that would halt the collapse before reaching the point of no return. He published papers attempting to demonstrate that rotating matter could never collapse completely, that various physical effects would always prevent the formation of these cosmic nightmares. The scientific establishment largely agreed with him. Black holes seemed too strange, too violent, too contrary to common sense to exist in the real universe. They were curiosities for mathematicians to explore, not phenomena that astronomers expected to find. The phrase black hole didn't even exist yet. Physicists referred to these theoretical objects as frozen stars or collapsed objects, and most believed they were probably impossible. Einstein's resistance to black holes reveals something profound about the relationship between theoretical physics and physical intuition. Even the greatest scientific minds can struggle to accept the full implications of their own discoveries. Einstein had revolutionized our understanding of space-time and gravity, yet he couldn't bring himself to embrace one of the most startling consequences of his revolution. His equations were telling him that the universe contained regions where causality broke down, where the normal flow of time ceased to have meaning, where the very concept of spatial distance became meaningless. These weren't just extreme physical conditions. They were tears in the fabric of reality itself. As the decades passed, other physicists began to take black holes more seriously. In the 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar calculated that there was a maximum mass a star could have and still be supported by the pressure of its own nuclear reactions. Stars more massive than this limit, now called the Chandrasekhar mass, would inevitably collapse under their own gravity when their nuclear fuel ran out. No force in the universe could stop this collapse once it began. The implications were staggering. The cosmos contained billions of stars massive enough to become black holes. As these stellar giants aged and died, they would compress into points of infinite density, creating invisible gravitational traps scattered throughout the galaxy. Yet Einstein continued to resist this conclusion, publishing papers as late as 1939 arguing that rotating stars could never collapse completely. Meanwhile, advances in astronomy were beginning to reveal phenomena that seemed impossible to explain without invoking Einstein's mathematical nightmares. In the 1960s, astronomers discovered incredibly powerful radio sources in distant galaxies. These quasars, as they came to be known, emitted more energy than entire galaxies of stars, all from regions smaller than our solar system. No conventional energy source could account for such prodigious output. The only plausible explanation was that quasars were powered by matter falling into supermassive black holes, releasing tremendous energy in the process. The universe was not only stranger than Einstein had imagined, it was stranger than he could bear to imagine. His beloved cosmos, governed by elegant mathematical laws, contained regions where those very laws ceased to apply. Space and time, the fundamental coordinates of existence, could be so severely warped that they lost all meaning. The idea that such cosmic monsters might actually exist filled him with a kind of intellectual revulsion that persisted until his death in 1955. Today, we know that Einstein's nightmares are among the most common objects in the universe. Every large galaxy contains a supermassive black hole at its center, some containing billions of times the mass of our Sun compressed into regions smaller than our solar system. We've detected the gravitational waves produced when two black holes spiral into each other and merge, creating ripples in spacetime itself that stretch and compress the entire universe by amounts smaller than a proton's width. We've used networks of radio telescopes spanning the entire Earth to photograph the shadow of the supermassive black hole at the center of a distant galaxy, revealing the dark silhouette of the event horizon against the glowing matter spiraling toward its doom. These observations have confirmed Einstein's equations with extraordinary precision, while simultaneously validating the predictions that terrified him. The mathematical monster he tried so hard to banish from his theory has proven to be one of the most important and ubiquitous phenomena in the cosmos. Black holes aren't cosmic aberrations. They're essential components of galactic evolution, the engines that power quasars, the gravitational anchors around which entire star systems orbit. The story of Einstein's relationship with black holes teaches us something profound about the nature of scientific discovery. Sometimes the most beautiful and successful theories lead to conclusions that challenge our deepest intuitions about the nature of reality. The equations don't care whether their predictions seem reasonable or comfortable. They simply describe what is, regardless of whether we find those descriptions aesthetically pleasing or philosophically satisfying. Einstein's terror also reveals the fundamentally human dimension of scientific progress. Even the most brilliant minds are constrained by the limits of imagination and cultural expectation. The same intellectual courage that allowed Einstein to overthrow Newton's conception of space and time seemed to desert him when confronted with the full implications of his own revolution. He could envision curved spacetime and relative simultaneity, but he couldn't accept cosmic regions where the very notion of physics broke down. Modern research has revealed that black holes are even stranger and more important than Einstein's generation could have imagined. They don't just warp spacetime around them. They actively participate in the evolution of galaxies, regulating star formation and influencing the distribution of matter across cosmic scales. The supermassive black holes at galactic centers aren't static monsters consuming everything around them. They're dynamic participants in cosmic ecology, sometimes dormant, sometimes violently active, always intimately connected to the stellar communities surrounding them. Recent theoretical work suggests that black holes might not even be the cosmic dead ends they were once thought to be. Some physicists propose that what appears to be a singularity from the outside might actually be a kind of cosmic gateway, a region where the normal rules of spacetime give way to something even more exotic. The mathematics of black holes intersects with theories of quantum mechanics in ways that suggest the information falling into a black hole might not be lost forever, but rather transformed and eventually released through subtle quantum effects. These developments would have both fascinated and terrified Einstein. His equations continue to reveal new cosmic possibilities that push the boundaries of physical understanding. Wormholes, theoretical shortcuts through spacetime that could connect distant regions of the universe or even different universes entirely, emerge naturally from the mathematics of general relativity. The same equations that predict black holes also suggest the possibility of cosmic inflation, dark energy, and gravitational time travel. Each new discovery in black hole physics raises profound questions about the nature of reality itself. If space-time can be curved and warped, if regions can exist where time stops and space becomes infinitely compressed, what does this tell us about the fundamental structure of existence? Are space and time truly fundamental aspects of reality, or are they emergent properties of something even more basic and strange? The debate continues today among physicists wrestling with the quantum mechanical properties of black holes. Stephen Hawking's discovery that black holes slowly evaporate by emitting radiation has led to paradoxes that challenge our understanding of information conservation in quantum mechanics. If a black hole eventually disappears entirely, taking with it all the information about the matter that fell into it, this would violate one of the most fundamental principles of quantum theory. Yet if the information somehow escapes, we need new physics to explain how this is possible. Einstein died before these quantum mechanical complications became apparent, but he would have recognized the pattern. Once again, his equations were leading physics into territory that challenged basic assumptions about the nature of reality. The mathematical framework he created in 1915 continues to generate predictions that push the boundaries of scientific understanding, forcing physicists to confront ever more exotic possibilities about the cosmos we inhabit. The legacy of Einstein's struggle with black holes extends far beyond theoretical physics. It demonstrates the importance of mathematical rigor in scientific thinking, even when mathematics leads to conclusions that seem impossible or absurd. Einstein's equations predicted black holes decades before astronomers had any direct evidence for their existence. The mathematics was ahead of observation, pointing toward cosmic phenomena that wouldn't be confirmed until sophisticated instruments and techniques became available. This pattern repeats throughout the history of physics. Mathematical theories often predict phenomena that seem impossible given current experimental capabilities. Yet those predictions eventually prove to be accurate descriptions of previously unknown aspects of reality. Electromagnetic waves were mathematical abstractions in Maxwell's equations before Hertz demonstrated their existence in the laboratory. Antimatter was a mathematical necessity in Dirac's quantum mechanical equations before it was discovered in cosmic ray experiments. The story of black holes also illustrates the cumulative nature of scientific knowledge. Einstein's resistance to his own predictions didn't prevent other physicists from exploring their implications. Schwarzschild's wartime calculations, Chandrasekhar's stellar evolution models, and countless other contributions gradually built the theoretical framework that eventually enabled astronomers to identify and study real black holes. Science progresses not through the insights of individual geniuses alone, but through the collective efforts of communities of researchers building on each other's work across generations. Today, black hole research represents one of the most active and exciting areas of theoretical and observational physics. Gravitational wave detectors are opening new windows onto cosmic phenomena that were purely theoretical just decades ago. The Event Horizon Telescope is providing unprecedented views of the regions immediately surrounding supermassive black holes. Space-based observatories are tracking stars as they orbit the supermassive black hole at the center of our own galaxy, testing Einstein's predictions in gravitational fields billions of times stronger than anything available in terrestrial laboratories. These observations continue to confirm the accuracy of Einstein's equations while revealing new cosmic phenomena that push theoretical understanding in unexpected directions. The mathematics that once terrified Einstein has become a roadmap for exploring the most extreme environments in the universe. Black holes have transformed from mathematical nightmares into cosmic laboratories where the fundamental laws of physics are tested under conditions that cannot be replicated anywhere else. The profound irony is that Einstein's mathematical nightmare has become one of humanity's greatest scientific triumphs. The cosmic phenomena he tried so desperately to disprove have opened entirely new chapters in our understanding of space, time, matter, and energy. Black holes have revealed connections between gravity and quantum mechanics that continue to drive theoretical research. They've provided natural experiments in extreme physics that no laboratory could ever replicate. They've shown us that the universe is far stranger and more wonderful than even Einstein's extraordinary imagination could encompass. The terror that kept Einstein awake at night has become the foundation for some of our deepest insights into the nature of reality itself. His resistance to black holes teaches us that scientific progress sometimes requires us to accept conclusions that violate our most basic intuitions about how the world should work. The universe is under no obligation to conform to human expectations or aesthetic preferences. It simply is what it is, regardless of whether we find its properties comfortable or comprehensible. As we continue to probe the mysteries of black holes and the extreme physics they represent, we honor both Einstein's mathematical genius and his very human struggle to accept the full implications of his discoveries. The equations he created in 1915 continue to guide our exploration of cosmic phenomena he could never have imagined. His mathematical framework has proven robust enough to describe everything from the gentle bending of starlight to the violent collision of black holes billions of times more massive than the Sun. The story of Einstein's nightmare reminds us that the greatest scientific discoveries often emerge from the courage to follow mathematical reasoning wherever it leads, even into territories that seem impossible or terrifying. The universe revealed by modern physics is stranger than fiction, populated by objects and phenomena that challenge every assumption about the nature of space-time and reality itself. Yet this strange universe is also governed by mathematical laws of extraordinary beauty and power, laws that continue to guide our exploration of cosmic mysteries we are only beginning to understand. Einstein's equations, born from his struggle to understand the anomalous orbit of Mercury, have become humanity's most powerful tool for exploring the cosmos. They've revealed a universe far richer and more complex than Newton's clockwork cosmos, a dynamic space-time arena where matter and energy dance with gravity in a cosmic ballet of extraordinary complexity and beauty. The mathematical nightmares that once terrified Einstein have become our windows into the deepest mysteries of existence itself.